All right, this lesson is on potential energy diagrams.
You just started. That's the reason why I did it.
I'm leaving it in. Okay, this is on potential energy diagrams. Potential energy diagrams sound really scary. They can be really scary, but once you get the hang of them, I promise it's super easy. So here we go. In a potential energy diagram, we are talking about energy that's stored in chemical bonds. Potential energy and chemical energy are just about the same thing. And the more potential energy something has, usually it is more likely or willing to react. I banged my tooth. This is already a bad video. The potential energy diagram is going to track energy changes during a chemical reaction. So you may think of a potential energy diagram and then your brain goes to a heating curve. Different things, pinky promise. So in a heating curve, what happens is you get let's see, you would get a ledge that looks like this, right? You have your solid heating, then you have melting, then you have your, oh no, that's not what I want to do. Then you have your liquid phase, then you would have your boiling phase, and then, or phase change rather, and then here is your gas. This is a heating curve, and this applies to physical changes, because all of these that we're talking about are physical changes. Changing from a solid to a liquid in melting, that's a physical change. If we look at going from a liquid to a gas in vaporization, that is also a phase change. This is a heating curve, and it is used for physical changes. And those physical changes are specifically phase changes. And that's not what I'm talking about here. Just want to make it clear that they're two separate things. So in a heating curve, physical phase changes, and in a potential energy diagram, we are tracking what is happening during a chemical reaction. That is the important part here. During a chemical reaction. Let's highlight that. If we have a chemical reaction, what we put in is different chemically in terms of a formula, in terms of bond, from the things that we end up with. So enthalpy is kind of what's most important in a potential energy diagram. If you remember, when we break bonds, energy needs to be absorbed. And when we form bonds, energy is released. So every time that we are breaking and forming bonds, we are either absorbing or releasing energy. And it's never really that easy that just a chemical reaction, we're only forming bonds. That virtually never happens. It's usually a mixture of breaking bonds and forming bonds. And in that, we have a combination of absorbing energy and releasing energy. Enthalpy, which is also called the heat of reaction, or delta H, that is going to tell us the overall loss or the overall gain of energy by the end of the reaction. And we can calculate this by finding the difference between our starting point and our end point. If you want it specifically in math terms, it would be delta H is equal to the products, or the potential energy of the products minus the potential energy of the reactants. Part of this is because delta in science means change, and delta is usually calculated by doing final minus initial. In chemistry, our final thing is the products and the initial thing is the reactants. So that's where that comes from. That slide showed up twice. That's fun. Okay, so in an exothermic reaction, we are looking at an overall loss of energy where energy is exiting the reaction, and we wind up with a negative delta H. And something interesting is that when I write an equation, I could write heat or I could write some number of kilojoules, and that would be on the right side of my equation, indicating that it was coming out and it was a product of the reaction. And the opposite is true as well. For an endothermic reaction, the heat is entering, and therefore it would be Oh, I just wrote right 2 times. This would be on the left side, excuse me. That would be on the left side of the equation, meaning that it had to go into the reaction to get it to happen. It would act as if it were a reactant, and that would result in a positive delta H. Okay, so the amount of energy that I need to start my reaction is called the activation energy. It seems pretty straightforward, but it also can seem kind of confusing. So if I have a sheet of paper and I want to light this on fire, I can't just and then it's on fire. I have to have some type of activation energy to get this on fire in a combustion reaction. So I would maybe strike a match, and that striking of the match would be the activation energy I needed to get this to light on fire. Well, it would light the match on fire, and then I would just, get this on fire. But that's the gist of it. Some things need a little boost before they react. Things that you can just put them in contact with each other and then all of a sudden they're reacting, that is an exceptionally low activation energy. A lot of things do need a little kick to get them moving. So, nature does like one of these reactions more than the other. Nature really prefers exothermic reactions. And the reason for that is because nature is looking to get rid of energy and not hold on to it. So when you see the graph, it may make a little bit more sense, but what happens is that as we are losing energy, what happens is the reactants started, we'll say, with 10 kilojoules of energy, and then our products would end up with, I have this backwards. It would be, let me see if I can draw it. We would have, products that have 10 kilojoules of energy and then reactants maybe that had 15. I don't know if you're going to see that. Oh, no, you're seeing it backwards. Great. Okay. Useless. I'll show you on the graph. The idea is that we want our products to have as little energy as possible. Nature wants to hold on to as little energy as possible. So that's why an exothermic is favored, is because you're getting rid of that energy. Now, another thing. If we add a catalyst, it makes our reaction happen easier. You learned that during the collision theory lesson. So if we add a catalyst, what happens is that it takes our activation energy and it shrinks it. So this solid line is the path that my reaction would take if I did not use a catalyst. And you can see that when I use a catalyst, this reaction is actually using less energy, and it's happening using less energy. And that is thanks to the help of a catalyst. So you have this diagram, and I'd like to go over the pieces with you. This would be a potential energy diagram. This part right here is showing us how much energy the reactants have stored in their bonds, meaning that this box is showing us potential energy, and that is going to be measured in kilojoules, lowercase k, capital J. That is how much energy we have stored here, okay? And across the x-axis, we have, it can be written one of 2 ways. It'll be written as time, or it'll be written as the reaction coordinate, which is essentially the progress of the reaction. So we start our reaction with reactants that have some amount of energy holding them together. That's their potential energy. It's the energy in the bonds between the atoms holding them all together. Now, I'm going to give my reaction a little bit of activation energy. And what this does is it's just going to add just the amount of energy I need to get my reaction moving. The reaction really starts at this star at the top of the graph, and that is called, I'm sorry, I hate this font. It is called the activated complex. It's also sometimes called the transition state, but I don't like that phrase as much. So we're going to stick to activated complex, but you can see it as a transition state. And this is the part where your reaction is actually happening. Your reactants are in the process, literally, of becoming products. It's a split second. It's super high energy. Usually you have too much stuff in too small of a place, and that's what makes it high energy. As soon as your reaction is finished, you are left with the products, which have some amount of energy stored in their bonds, which is shown right here. And I can figure out exactly the net usage of energy in this reaction with delta H, which is right here. Let's make this readable. Why is this being funny? I want it in the center of the box, please. Oh boy. Okay, regardless. This is delta H. Can we make this font black, please? Thank you. Okay, so delta H is going to show us how much energy was either lost or gained during this reaction. Now, let's just put numbers on here for shiggles. So this right here is, let's say, 20 kilojoules. I have 20 kilojoules of energy stored in the bonds of my products. And we can also say that maybe up here in line with my reactants, I have 80 kilojoules. So if I wanted to come to the side and I wanted to calculate delta H, I could do that quite easily. Delta H, you should remember, is equal to the potential energy of the products minus the potential energy of the reactants. And in doing this, I can look at the graph and figure out whether my reaction is gaining or losing energy overall. Here we had to gain a little bit, you had to add a little activation energy. We want to figure out the net, the total. So the potential energy of my products, you can look at the graph here, that is set for 20 kilojoules, and I can subtract the potential energy of my reactants, which I read from the graph is 80 kilojoules. 20 minus 80, you should know, is negative 60 kilojoules. Now, if my delta H, or my heat of reaction, is negative, it means overall I've had a loss of energy, making this an exothermic potential energy diagram. Okay, if you're not with me, backtrack and rewatch it. This is exothermic because I had a negative delta H, and negative delta H's are indicative of a loss of energy. Okay. Once you're here, you should be able to fly through the endothermic quite easily. So endothermic, still, this is going to be, this is still going to represent time, or the reaction coordinate. This will still be the potential energy in kilojoules. Now, you may notice some differences here. My reactants have less energy stored in their bonds than they did on the exothermic graph, which means I need a bigger activation energy to get this to happen. This is another reason why nature favors exothermic. Nature only has to add a little bit of energy to get an exothermic reaction started, where an endothermic requires much more energy. So this will still be my activation energy. Which in this case is just much bigger. And then here, the star, the tippy top of the graph, is still going to be called the activated complex, sometimes called the transition state. And that is where the reaction is happening. It's where my reactants are transitioning into products. So it's a lot of stuff stored in a very small space. Sometimes you have atoms with extra bonds, more than they should, because they're losing one bond and gaining another at the same time. That's why it's high energy. And then once the reaction is over, we have our products. And that means that this right here is still delta H. It's just in this case, our delta H is a little bit different. Oops. Okay, so we can again add some numbers to our graph. This is a lower number. Let's say that this one is, I don't know. Let's give some new numbers. Let's say 30. And then up here, we can say that our products have maybe 80 kilojoules of energy stored in their bonds. So I'm just going to copy this and move it here. And I'm going to take out these numbers because this is not right. So I want to calculate my delta H. Delta H is still going to be my potential energy of the products minus the potential energy of the reactants. In this case, my products are 80 kilojoules, which you can see right here. I can subtract the potential energy of my reactants right here, which is 30 kilojoules. And when I subtract these, 80 minus 30 is 50 kilojoules, and that is a positive 50, meaning that overall, oh, it thinks I'm doing bullets. I'm not doing bullets. This means that overall, even though I had to gain and lose energy, I have overall gained, which would mean that this is an endothermic potential energy diagram. Now the fun part. A lot of these PE diagrams can be read both forwards and backwards. So if you're in my note sheet, you know that this and this are right beside each other, and you should notice that they are mirror images. So if you were to flip the endothermic and read it backwards, that would mean that these are now your reactants, and then these would be your products, right? And we can just get rid of this box altogether and this box. So if you read this backwards, this would actually be a small activation energy. Your reaction happens, and overall, you would have an exothermic reaction. You read it backwards. Instead of doing 80 minus 30, you would do 30 minus 80. You see this? This is where it gets interesting. I'm going to put it all back to normal. Oh, wait. Too far. Okay. So you can read these both forwards and backwards. And then if I were to add a catalyst, I would actually get something like this, where I have a smaller activation energy. My new activation energy would actually go from here to here. Can I make this arrow straight? Thank you. So this would be my new activation energy with a catalyst, instead of it being this tall. So let's color code these. We'll say that the blue arrow, also make this a little thicker so you can actually see it. The blue arrow is the activation energy without a catalyst, and the pink is with. So you can see literally a catalyst saved us 40 kilojoules of energy just by using it. And then our activated complex, which is the tippy top of the graph, that guy is also saved 40 kilojoules of energy just because of the use of a catalyst. So that means that this reaction is going to happen easier, which means more effective collisions. Let's see. We talked about a catalyst. We talked about going both forwards and backwards. One last thing. When you look at a graph, it can sometimes be difficult to point out whether it's endo or exo, especially if the graph doesn't have numbers on it. So I have a trick for you. If you're looking at this graph and you think of it as a roller coaster, this would be a very exciting roller coaster. And an exciting roller coaster would be an exothermic potential energy diagram. So that is all. The puppy is fussing. He wants dinner. So I'm going to call it here. Any questions, leave them in the comment section and I will get back to you.